When you try to do principal component analysis in R, or in other languages for that matter, you often find that there's a bunch of different routines that are kind of built into the libraries or the easy to find libraries that claim to do principal component analysis, but seem to be somehow different. In our last lecture, we saw two. One was really dated, and if you look in the help file, it even tells you kind of not to use it. And the other one was newer. And today we're going to explore the differences between these particular two principal component analysis algorithms. And we're going to try to understand, why is the newer one quote unquote better? What advantages does it actually have? And we're going to end up exploring this topic called Singular Value Decomposition, which is a tool that's used in the newer algorithm, but it's also used in tons of other applications, not necessarily related to principal component analysis, or at least not in some obvious way. But so it's a tool that's used all over the place. And one part of it, or sort of an application of it, is we're going to see something called the pseudoinverse, which you might have been using but not even knowing, much like SVD or Singular Value Decomposition. You probably have been using it, not knowing it. But so this is a bit of a mathematical diversion, and we're just going to try to understand the details, or at least some of the details, of what's kind of under the hood for these, at least these two different types of principal component analysis algorithms. We're really just going to focus on the newer one and try to understand what advantages it has. All right, let's get started. Hopefully you remember from the last lecture, we actually saw two routines for doing principal component analysis in R. And I wanted to say something about the difference between the two in this lecture. But also, in a way, this lecture is really kind of about the advantages of one of them. So one of the routines that we saw was called Princomp. And that one, if you look at the help files, which you should do always, of course, when you're using routines for the first time, have a quick look at their help file to see if there's information in there that will be useful for you. So this one, if you read its help file, it says that it uses eigen, the routine that we've used to find eigenvalues and eigenvectors, on the output of the correlation matrix routine, I believe, to get its results. And it says in the description that the routine is old, or I don't know if it says old exactly, but what it says is kept around for the purpose of being compatible with an older language, for S plus. I don't know if you write S plus with all caps or not, compatibility. And it even says right in its help file that the other method, PRComp, is better. And so let's talk about that one, PRComp. Right? So PRComp, and again, this is a description from Princomp. It says a preferred method. They don't exactly explain how or why, but they do say that it uses a routine called SVN, or SVD, sorry. Singular Value Decomposition is what that stands for. And again, this is from the Princomp help file. And so probably you should just stop using Princomp unless you have some reason to be checking against some older calculations or something like that. So I would stick with PRComp. So use PRComp and not Princomp. But let's talk a little bit today about what is it talking about, this SVD thing, and why is it good. So that's what today's lecture is really about. So SVD, or rather, let's just call it by its full name, Singular Value decomposition. SVD for short. So singular value decomposition is a method that you'll see in a variety of different places. And I just kind of want to highlight today some of the advantages of it, or why is it useful, what is it good for. So this is a bit of a detour. It's a bit theoretical, this discussion, but this is a really common and powerful algorithm. Singular value decomposition is, and it finds application in a lot of different settings. There are also sort of many ways to introduce it, many ways to describe it. Or introduce it. Sorry. Bad writing. Really got to work on this. So in particular, I don't know if any of you use this book for references, but there's a very nice computer coding book called Numerical Recipes. It maybe is a little bit on the old side at this point. I don't know, but it's been refreshed many times over the years, and I find it really, among the various different books about numerical methods, to be one of the more clear and easy to follow. But in that book, Numerical Recipes, you'll find a description of it that's fairly different from the description that I'm going to give here. And I'm sure that if you dig around in many different linear algebra textbooks, you'll also find other ones. But I want to just sort of go through one of them today and talk about the details of what this thing is and why it's useful. So the overall goal is that you want to decompose an arbitrary matrix. That is to say, write it in terms of some other ones. So decompose an arbitrary matrix, which I think for us, you want to think of as like our X matrix, but we're going to call this M, so similar to X. And at the end of this, we'll discuss how do you apply this to principal component analysis. We'll do that at the very end of the lecture. But okay, so here are the general layout of things. Here's the general layout of things. So first of all, M is an n by p matrix. Right? It has eigenvalues lambda I, or rather, sorry, misspoke there. Lambda I are the eigenvalues of M transpose M, which is a P by P matrix. So these are similar to the principal component variances. Similar. We'll talk about that at the end. There are going to be, so let's say there are going to be R of them that are deemed non-zero. And I think the word deemed here is important because sometimes when you do a calculation of the eigenvalues, you find some that are really small, but not quite zero. And sometimes you have to decide, like, wait, how small is this small enough? Because if I carry on with this one, it's going to introduce a huge amount of round-off error because the scales are so different from other scales in my problem. And so you often are faced with that difficulty. So we'll say then R is the rank of M transpose M. And these square roots of those guys, square root of lambda I, these guys are called the singular values. of M. So that's what they're called. As just a name. And so you should think of these as similar to standard deviations in principal component analysis. Or rather, similar to the standard deviations of the data along the principal component axes. All right, and so the decomposition is going to work. So this is just the layout of the matrix that we start with and how we define its eigenvalues and so on. What we want to do is we want to decompose it with the following. We want to use some matrix that's R by R, and we'll call it D. And it looks like this. It's a diagonal matrix. And along its diagonal are square root of lambda 1, and then up to square root of lambda R. Right? So that's one of the matrices that's going to appear in our decomposition. We want to use that to define the matrix S, an n by p matrix. S. And so S is going to look like this. Now, so this will be a new way for us to write matrices. So there's up in the corner, there's the matrix D, right? Filling up a space that is R by R. And then around it are zeros, which I'll write like this. But this is sort of a schematic way of writing this. So let me move this guy like this. So this is just a schematic way of saying that these guys here, they fill the matrix up to the needed size, up to n by p. Right, because D is some square diagonal matrix that's R by R, and to get a matrix that's n by p, we need to just fill up the number of rows and number of columns as needed to get up to n by p. So it's not necessarily the case that there's just 1 0 here and then 2 down here. That's not what's shown here. It's just saying fill up that matrix until you get it up to size n by p. Right, so you can ask yourself, like, what are you gonna need to do this? All right, so are you gonna need extra columns? Of zeros, rather. And why would you need extra columns of zeros? So think about that. That means there's less than, so that means that R is less than P, right? In fact, I should have put that up here. So I'm going to put that up here. R of them are deemed non-zero, and so that means that R is in between 0 and P. That's an important point, right? And deemed is also an important point. They may actually be non-zero, all these things, or maybe some of them are close to 0, so far enough away from 0 that you declare them to be non-zero. But some of them you might chop off because you think they're too small. I don't want to mess with those. They're going to make trouble for me. And so you can ask yourself, like, well, why would I need extra columns of zeros? So the dimensions n by p are the same as the dimensions of the matrix M, right? So you might need some extra columns if you had some 0 eigenvalues, or if you just had some that you deemed close enough to 0 to treat as 0. So for this, the answer is maybe. If you had some 0 eigenvalues, or if rather they were so close to 0 you decided to count them as 0. But what about extra rows of zeros? That almost certainly, right? Because because you want extra rows to fill it out so that you have the same number of rows as your number of observations in your starting matrix M, which you should think of as kind of like our X matrix. And the chances of it would be a bad thing in the case. So these answers are for us, for our application. It would be pretty bad if the number of observations matched the numbers of features for us. Usually that's bad news. So almost certainly you're going to have some extra rows here, and maybe you'll have some extra columns if you didn't have sort of a full rank matrix or covariance matrix. Okay, so that's kind of where we are. So we've invented this matrix S out of the eigenvalues of the M transpose times M matrix. And so now we're going to make a claim that we won't prove in this class. So you can always find a pair of matrices and we'll call them U and V. And they're not unique, so there may be more than one pair. Maybe an infinite number of them, such that the following is true. Right, so I'm going to write out what you can do with these guys. The matrix that you started with can be decomposed like this. It's U times the matrix S, the one that we just built, times the transpose of the matrix V. And both U and V have the following property. So U is an n by n matrix and is what they call orthogonal, meaning U transpose is equal to U inverse. Make sure that that's clearly an inverse sign. And V is P by P and is also an orthogonal matrix, meaning that V transpose is equal to V inverse. Okay? And so just as an aside, right, so here's this little aside. A matrix is called orthogonal. So we'll say matrix Q is orthogonal. The better name might be orthonormal, I think, but we'll say orthogonal. If Q transpose is equal to Q inverse. And the matrix of loadings is an example. So I'll remind you what it looks like. Depending on how you wanted to name it, it's either A or A transpose. And A looks like this, right? It's got these unit eigenvectors, like this. Right? And then the transpose has those things as, so A itself has those things as rows. Right? Like so. And so you should be able to see that if you did this product, A transpose times A, right, and then let's just take a look at row I, column J of that. So if you stare at the way I've written those things up there, A transpose and A, it should be clear to you, or actually let's do it this way. It doesn't matter either way. I think it's easier to see it this way though. If you look at this thing, then you get alpha hat I dotted with alpha hat J. Right, and that's equal to the identity matrix, which is just ones or zeros. So it's 1 if I is equal to J, and 0 off the diagonal. Like that. So that matrix is called orthogonal because its rows or columns, however you want to put it, are perpendicular to each other. In fact, I think the name should be orthonormal. And it's also true, so similar for A times A transpose. And so that tells you that then A transpose is the inverse of A. So that was just a little aside. So where does that name come from, and where have we seen a matrix like this? Right, so that's what that little aside was about, orthonormal or orthogonal matrices. Okay, so now let's go back to our decomposed matrix, all right? So the decomposed form is quite handy. That's our whole point here, and useful. Sometimes it's also cheap to work with. Cheap to use. Cheap to do matrix multiplications with and stuff like that, or to invert, or who knows. And so let's look at an example. So first of all, just remember what it actually looks like. So, well, I'll write it in the example. Okay, so example. This one should be red. Pseudo-inverse. If you've ever looked up pseudo-inverse, you might have found some discussion of singular value decomposition. And so I'm going to talk about a little bit about that here and why it's useful, where you might have, you might be using these things already and not even know, because they're inside some algorithm that you've just been using. And so the idea is, look, so the matrix M looks like this, right? So M is equal to U in the decomposed form times S times V transpose. And let's just look at the dimensionality here to make sure we understand everything. So M has dimensions n by p, right? U has dimensions of n by n. S has dimensions n by p. And V transpose has dimensions p by p. Right, so that's the dimensionality of things. And so what we want something that's kind of like an inverse of M, an inverse like object for M, right? And M is not going to have an inverse in the normal way, right? Because what you need for an inverse is that a matrix times its inverse gives the identity matrix from either direction. And you need the matrix to be square for that to be possible. But we want to look for something that's kind of like an inverse. And so here, let's kind of just like discuss what it is we want. So let's just name the notation. We'll call M with a plus over it the pseudo-inverse. Of M, right? And so how will it look? So M plus will be the following, right? So it's U S V transpose plus, right? And we're going to suppose that the plus operates in the way that the normal inverse kind of operates, so that the inverse of a product like that is the product of the inverses but in reverse order. So what we have is V transpose plus S is in the same place, and then U plus, like that, right? And we want to enforce the rule that if a matrix has an inverse, so if Q has an inverse, then Q plus will just be equal to its inverse. Right, so we want to make that rule. And so that means we know what the inverses are for the first and last matrices there. V transpose is the inverse of V. So this tells us this thing looks like this. So V transpose is the inverse of V. So this is V times S plus. And then U, the inverse of U is U transpose. So this looks like this. That's a T, not a plus there. Right? And so what should S plus be? So you want to think about what do you get if you were to multiply M by M plus, or M plus by M, and so on. So this suggests ultimately, and then we can look back at why this is true. It suggests the following, so that S plus should be equal to something like this. The inverse of the matrix D, which D was square and diagonal, so it definitely has an inverse, but filled out like this. And what does it get filled out to? What are its dimensions? So I'm just going to write this filled to P by N. Right, so the opposite of the dimensions of M. Right, and what is the inverse here of D? So there's nothing funny about that. So D inverse, well, here, you want this to be true. Right, and so what does this mean? It's for D. So it means that D inverse is equal to the diagonal matrix of 1 over the square root of lambda 1, and then up to 1 over the square root of lambda r. Right, so remember all those lambdas are non-zero. So that's why D has a nice elegant, it's part of the reason why D has a nice inverse. And so let's take a look at, does this give us anything? So I said that this expression here suggests what you want for S plus, but let's just, maybe I jumped the gun a little bit. Let's see what happens if you multiply S by S plus and vice versa, right? So think about what this means. So S plus we've just seen, right? And so what does S look like? So S looks like D like that, and then filled in, so to N by P. And S plus we just saw, right, this is the inverse, and then filled to P by N with zeros, right? And so if you look at S plus times S, or let's first try S times S plus, right? So what do you get? In the top, so these guys come over here and multiply this, and so on. And so what you're going to get is something that has dimensions n by n, right? S times S plus, so this will have dimensions n by n. And in the top corner of it, there's going to be an identity matrix of size R. So I'll just fill it in like this. To n by n. And where IR is diagonal with R times R of these guys. R1s. R1s? They are ones. It has the number of ones down the diagonal is R. Okay. And so this is not an identity matrix, right? S times S plus, but it is a sort of identity-like matrix. It has an identity matrix up in its corner, and then it's filled up with zeros to get it to whatever dimensions you need. and S plus times S, right? So that's the opposite. That's going to be P by P, but it's otherwise the same kind of filling. Oops. That I'll just write like this. These zeros, remember, are kind of symbolic. So these are 2 P by P. All right, so in this sense, S plus is sort of like a pseudo inverse of S, because so it's not an inverse in the usual way, because if you multiply it by one side, you get a different matrix than if you multiply it by the other, right? And neither one is an identity matrix. The identity matrices are always square. So neither one of these is a square identity matrix, but they're sort of like filled to make the right dimensions. So I hope that's kind of clear. And let's try to use this, all right? So you can use this in linear regression. Right, a familiar, hopefully, algorithm or a tool that you guys might use. Right, so you can use it in linear regression to sort of invert, to pseudo invert, all right, the following expression. Let's say you have a vector of responses equal to some data matrix times a vector of parameters, like that. All right, so that's linear regression, like this. And I'm going to move this over to the left because I want to sort of make a comparison here. And so you can kind of, quote, invert this by multiplying on the left by x plus. And then, so what you get is, how do I say this? So you get something kind of like a collection of betas, where beta is now going to be equal to V times S plus times U transpose times Y. Sorry, that's a vector Y. Right, now compare that to what you get when you do the sort of standard kind of least squared method. So compare to the following, where you get beta, the estimators. So usually people put a hat on this, I think, but I've been using hats for something else, and I don't want to have multiple labels on top of this guy. And so the normal, if you look back to an earlier lecture, we did this. So you have x transpose times x inverted times x transpose times y. Now that's fine, but to do it, you have to invert this matrix. And sometimes, if there are eigenvalues of that covariance-like looking matrix that are near zero, that inverse is going to blow up, right? So the advantage here is that on the left, over on this side, you can look at your eigenvalues right away and say like, oh, well, some of these are so small, they're going to make trouble for me, so I'll just throw them out. And so you're going to like have this dimension R is going to be less than P, and you'll get some parameters. You won't get the full set of parameters. So your beta will not have the full, like they'll have a lot of zeros in it, but the ones that you get might be better calculated, or might be less disturbed, less ruined by the nearly zero valued eigenvalues. And so this can be cheap, right? So this can be cheaply done. And I often say this in this lecture, that it can be cheap with the understanding that maybe somehow it was cheap to compute the decomposition, so to find V and U and S plus. So it can be cheap, but maybe the more important thing, and it allows for sort of dropping, it allows you to do the following. So you say like, oh, I had these eigenvalues. There was a collection of P of them normally. And then I just shrink it. Like that. So I drop a bunch of them so that I keep things manageable. And hopefully, so what we've done is, if some of those, of the lambda i's, were sort of near 0, and they would normally like blow up the usual, like the inverse process, right? Because the inverting of that matrix involves, so you may get a determinant that's very near 0, and the inverse of that matrix is proportional to 1 over the determinant, and so that just leads you to all kinds of trouble. So this is an application that you might have already been using. I don't know, if you dig through the help files for your linear regression algorithms, you might find singular value decomposition mentioned as being used, and that might help you understand kind of the output you're getting or why it's useful, and so on. Okay, but now let's try to apply it to principal component analysis and talk about how it works. So SVD in PCA. It's just an acronym zoo here, right? So what's going on here? So there's sort of, we're just going to try to link up the different notations so you can understand what refers to what. And hopefully I won't make any mistakes in that, but that's not really the important part here. The important part here is to understand what do you get out of doing this. All right, so anyways, let's try to link up the notation. All right, so first of all, we're going to make the matrix M equal the centered version of the data. So that's n by p. That's not a surprise, hopefully. And I want you to recall that this matrix, sigma, the covariance matrix, so 1 over n minus 1 x-centered transpose times x-centered, this guy is diagonalizable. Right, so that means it can be written in the following form. It can be written as this. Right, so we'll say sigma is equal to A transpose times L times A, where L is some kind of diagonal matrix. And these guys are the eigenvalues of sigma, right? All right, so now substitute in, so sub in this guy, the singular value decomposition version of x. All right, so let's do the substitution, where again, so here S is equal to diagonal of, how do these look? These are the square roots of lambda 1. So it's close, but, and it only goes up to R, right? All right, so you sub that in, what we get is on the left, so I'm going to substitute in, I've got, this guy is going to go on the left, and this guy is going to go on the right. So I hope that's clear. So on the left, I've got A transpose L times A. And so on the right-hand side, I've got 1 over n minus 1. And then I put in this for xc in here, right? So I got 1 over n minus 1 A transpose L times A transposed times A transpose L times A. Right? Oh, sorry. Yeah, I tend to go in loops with this. Sorry about that. Let's take those out. I'm subbing in the wrong thing here. And I think that was even wrong. What I want to substitute in here is this guy, right, for x. So sorry about that. So we've got U times S times V transposed, quantity transposed, times U times S times V transposed. Okay, so now we'll do the transpose on the right-hand side. So the 1 over n minus 1 is here. And again, the transpose flips the order and then transposes everything. And so what we get is V S transpose U transpose. Like that, all right? And so this, when you rearrange it, looks like V times S transposed S over n minus 1 V transposed. And that's because U transpose is the inverse of U here, right? And so this thing works. This expression is satisfied by the following, right? So first of all, if you compare these things, V should be equal to A transposed, right? And L should be equal to S transpose S, which is sometimes called S squared, over n minus 1. And so this is diagonal lambda 1 over n minus 1 dot 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 lambda r over n minus 1. Okay? So I hope I got all those things right and I didn't miss like a square root or an n minus 1 somewhere. That sometimes happens. But again, this is not the key point here. So what's key to understand, so first of all, so if you do this right, so if you have a cheap way to do this, a cheap way to decompose things, to find your U and your S and your V, right? So if you have a cheap way to do that, it tells you right away, then you have a cheap way, so it tells you these things, L and A transpose. And these are the ingredients for PCA. Right? And it also tells you why. Not in the philosophical sense, but it also tells you the matrix Y, right? Because look, so Y is equal to X times A transpose. And if you go ahead, so remember that's the rules for how you get into the PCA frame. And so let's just say again, if you do this, if X goes to X centered, right, then what we get here is Y is equal to X centered A transpose. And then if I put in my decomposed version of X, or X centered, what I get is U S V transpose times A transpose. And if you go back up here and see, well, V is A transposed. So V transposed is A. And so this gives me U S A times A transpose. And A times A transpose is the identity matrix. And so this is U times S, right? And what does this look like? So it looks kind of like this. So we've got like square root of lambda 1 times a column of the U matrix, like this. And it has R elements to it, but you can fill it to zeros. Right? And then the next one is all the way up to, again, I hope I got the square roots in the right places and stuff here. That's not the key issue here, though. The key issue is that you've got this nicely constructed thing, and then zeros over here as well. And the zeros, again, kind of fill things out. This is just kind of this block notation. So this is fill to n by p. And I should also say this guy is column 1 of the matrix U. So that notation, I hope it's clear. Yeah, and so this gives you this nice way to immediately generate the matrix Y. And you can, I'm not sure, so I'm not like deeply experienced with the nitty-gritty details of the singular value decomposition algorithm and its advantages. But what I can see by looking through this discussion is you clearly have like an advantage. So I'm not, what I meant by that, not super experienced with, I'm not totally familiar with like the scalings of the computational costs for computing the singular value decomposition as opposed to some other decompositions or inverting things or something like that. But what I can see is present in the singular value decomposition routine is some way to sort of like clip off eigenvalues that might have been problematic, and I would end up with a sort of different output as a result. But I've done it in some kind of like, yeah, I don't want to make trouble with these funny dimensions or something like that way, so that's somehow helpful. I hope you enjoyed that little mathematical diversion or sort of side exploration. You can go pretty far with those, and I think this one was a pretty interesting topic to check out. In the next lecture, we're going to see a little bit of a kind of a warning or a pitfall of something to look out for when doing principal component analysis. But then we're going to do a bunch more example work using R. I'll see you then.